Okay, that should be them up now, hopefully.
Super, you're good to go. Just for anybody that's just joined, please could we ask you to turn your cameras off? Thank you.
So, good evening. Yeah, 5 o'clock is good evening. My name's Colin McAteer, currently working as Principal Engineer in the Track Technical Authority, and I look after the survey and geometry team. So, presentation today is on photogrammetry. It's a bit of technical, it's a bit non-technical. There's a lot of, emphasis on drones and what we can do with drones. And some of those, I think it's just a good idea just to understand how we're getting the answers when we're using just photogrammetry. So this goes through it, some pros and cons, and it kind of leaves you up to make your own mind at the end. So a picture is worth 1,000 words. Yeah, that's one of those sort of home truths. It's ever since there've been pictures, they've been really handy. It's over 100 years ago. It is why we as engineers use drawings and not text. Those of us who work with standards, you'll know that you can write a standard and two folk will have two different meanings. Sometimes two folk can have three different meanings of what the standard says, but when it's a drawing, it's a drawing. It's fairly definitive. Photographs are the same. It's a record in time. It's definitive proof of what was there or what wasn't there at the time of the photograph. The other adage that goes about is the camera never lies. Well, that was true when we had film cameras. Today, yeah, I don't know. If the camera does lie, either that there's a lot of folk who now have dog ears and butterflies on their nose and things like that. So it is hard to distinguish between what was original, what was improved, has something been airbrushed out, has something been added in, so on and so forth. But manipulating a camera image, a photograph, is nothing new, and there is a whole branch of geomatics dedicated to it called photogrammetry. So a wee bit about the origins of photogrammetry. It goes back to mid-1800s, although Da Vinci first mentioned the theory of perspective way before that. And the idea in the mid-1800s was, back then surveying was kind of done by climbing up to the highest point in the village, generally the bell tower, and using a sextant to actually measure angles. And you plotted those. You went to the next village, you plotted those, and where the two lines intersected, that's where you knew the third village was. So the farthest you could survey was the farthest you could see. The farthest you could see was generally due to the elevation. How high could you climb? So people started using hot air balloons. Oh, this is quite good. I can get up higher, but I'm kind of moving. So when cameras came in, it became fairly obvious that this technique was, would be developed further. Little terrible joke there about it wasn't until the Wright brothers that aerial photography really took off. So modern photogrammetry still applies the same basic principles. We're comparing two photographs from two different positions. It's essentially not changed much since back in the 1800s. So there is a number of advantages in using photogrammetry in the real environment. Capture can be rapid. We can cover potentially miles of tracks in single missions. There is limitations. I'm not just talking about drone photography here. We've got fixed wing, we've got helicopters and stuff like that. It can be inexpensive. It's inherently safer because it's a remote sensing application. So boots are off ballast, especially if our ground control is established off track, adjacent roads, that type of stuff. And the output can be simple to interpret, especially if you're not an engineer who's used to working in plan and elevation drawings. And even if you are an engineer who's used to working in plan and elevation drawings, if you're working with a topographic survey, you're only getting the outline, the wireframe of the points that the surveyor's picked up for you. You don't really get a good feel for what the site's like. So it does sound like a bit of a survey bullet, a bit of a silver bullet. So why is it not adopted as our go-to source for topographic survey? And the devil is in the detail. I'm going to try and explain a little bit of what sits behind it, why there is wiggle room, shall we say, within photogrammetry. So I hope you've got coffee by your sides, because this gets a little bit heavy on the maths now. I've tried to strim out as much as possible. There's a few points here that I'll keep going back to. So I've brought them out up front. So you'll see mention things like principal points or optical centers. You'll hear me talk about oblique imagery, nadir imagery, overlaps, and stereoscopic. So essentially what we've got here, if you imagine that ellipse there, that is the lens of the camera. Everything inside the black box is inside the camera. Everything outside the black box is the ground. Okay. And the first principle in photogrammetry is that it's similar triangles. You can see there, point C refers to point C, point A refers to point A, point B refers to point B. They're used large letters and small letters. As you can see, they're also flipped. If you can imagine the distance between the focal length changes, then your footprint down here is going to get shorter. Again, if it increases, so on and so forth. And this is the symbol triangle principle. I've got 2 points in the ground. Those points go through the lens and are inversed and projected on the film. So saying there, once we know what the distance between the 2 points are on the ground, for a little bit of ground truthing, we can then work out what our scale is in the film. And once we've established that, providing that ground is flat, you can work out the scale factor for any other point on the ground. Essentially, you've got that distance. In the rail, it's quite handy if you've got a perfectly nadir, which is a straight down image, and we've got 2 rails, we know they're 1435-ish apart, so we can use that as our ground truthing, and then we can find out where everything else is. Maybe sleepers are a better bet because they're 2.5 meters and less likely to vary. I just have to move this little box. So just taking that concept another step forward, just to show that, whilst it works once, it doesn't work constantly. We've got the exact same here, like points 1 and 2, 3 and 4, they go up and they transfer across, as you can see in the top image. But when we go and actually look at that image, you can see here that 3 and 4 are actually over a hill, and 1 and 2 are further down. So the distance between 1 and 2 isn't the same distance between 3 and 4, because 3 and 4 are closer to the camera, but we don't get to see that within the image. So essentially, we've got a scale factor. If we work out the scale factor of 1 and 2 and apply it, that scale factor, I'm going to apply to 3 and 4, will give you an incorrect distance. So we need to understand where things change within the image and where we have to recalculate and rebaseline our scale factors. So even a very simple, car park and industrial building, that will have a minimum of 2 scale factors, one for the car park and then another one for the flat roof on the building above. It's unlikely that you've only got 2 things in one image. If you imagine even in the rail corridor, how many things we may have, you might be quite lucky. You might just have your track with no signalling, no overhead line, no line side furniture, just twin tracks. In which case, you don't have kind of one scale factor to worry about. So how do we work out from a flat image if we have varying heights? Okay, you can kind of interpolate it, you can kind of see it. Sometimes it's not that easy to see, but there is a principle within photogrammetry called relief displacement, and that's what I'm kind of showing here. So I mentioned principal point earlier on. That's essentially right in the middle of the image. Back in the old days when film was used, we had fiducial marks which were in all four corners, and then you basically drew between those and then drew between the diagonals, and that gave you a principal point. So what vertical displacement is, and you can see it in the little photograph here, it occurs in a radial line. So you can see that all of these are lying in the same orientation. They're all lying in the same direction. And the larger the item is, the greater the vertical displacement is. So hopefully you can see that that generator has got quite a small line compared to what looks like an REB, which has got a slightly larger line. So you can tell that that generator is greater than, that generator is smaller in height than the building. And that building is slightly higher, slightly smaller in height than the main building, and the lamppost is roughly about the same height. So you can get, just from a single photograph, you can get an estimation of differences in height. So that's quite handy. So even, if I'm looking at just that single image, I would need to do a scale factor for the ground, a scale factor for the generator, a scale factor for the building, REB, a scale factor for the main building. Potentially, if I'm really interested in the height of the lamppost, I might need to do a scale factor for that. I haven't marked up the hedge line, but you could, if I wanted to know the hedge line, I need to work out the scale factor for that as well. So you're starting to get multiple calculations in a single image. So here we get into sort of the more, where it gets even more complex when it comes to photogrammetry. I've mentioned similar triangles. I've mentioned relief displacement, and you can measure and you can take, coordinate things, but you require that image to be looking straight down. If it's not looking straight down perfectly nadir, and we're talking about aerial imagery, so there will be some pitch, roll, or yaw, probably a combination of all three. We have to know what those values are and remove them. It's a bit like we've taken those 2 points in the ground, but if we are slightly off, it's when the sun catches your shadow and casts a angle shadow in the sun. Nobody's legs are that long. So if you don't understand how well the angles have been calculated of pitch, roll, and yaw, or your sensor hasn't picked them up to the right precision, you're introducing errors into the results of your photogrammetry. So what we try and do with those, once we have those values of pitch and yaw, we look to do a thing called ortho rectification. And you can see here I've got two images, the exact same. One's processed and one's unprocessed. The one on the left is unprocessed. One on the right is processed. You can see the lamppost on the processed one. You struggle to see the lamppost, whereas in the original you can see it's quite clearly leaning out. I don't think that slide was supposed to be in there. So I'm going to talk a little bit about stereoscopic photogrammetry. And this is where we get our depth perception. We can use relief displacement, but this is slightly better. So I don't know if anyone wants to try this. Feel free. There's a little bit where you can get to go and so you can maybe do it later on. But it is how our eyes work as humans. They work. Most of those work with depth perception. It's how we're able to judge things like catching balls or not walking in and stuff. Different speeds and stuff like that. So as I said there, if you want to, you can close your eyes and have an object on your table and try and touch it if you open just one eye after closing both for a while. So the principle behind that is a thing called stereoscopic parallax. So hopefully we've all used optical dumpy levels. And you're used to seeing, the first thing you had to do was hold your little book in front of it and move your head about to make sure that the image didn't move or the lines in the level didn't move as you moved your head. Essentially, we were removing parallax. It's the same thing with looking at sleepers, as they go past you on a train, they're moving at really high speed. Buildings don't seem to move as much. So using stereoscopic parallax, we can tell if something's closer or further away. So part of the reason why we need the parallax is important to us is we need overlapping photographs. If we've only got a single photograph, you're kind of relying on just the relief displacement. And whilst relief displacement is good, the closer you get to the center point, the less you'll have. Again, going back to the shadows, it's a bit like the sun being at midday and you're on the equator, you don't cast a shadow because it's directly above you. So you can't always rely on relief displacement. Oh, these are getting a wee bit more wordy. So application of trig, first remove any pitch, yaw and roll, and then calculate the appropriate scale, correct for displacement, and then using differences in position from subsequent photos, it is possible to extract coordinate values in the X, Y, and Z. Photogrammetry really came into its own during, I think it was the Second World War, might have been the first. Although I think aerial recon probably wasn't as developed then. It's a technique that's been used for mapping. Ordnance Survey is their national mapping agency, and they use photogrammetry for the vast majority of their works. It gives you that unhindered view of the subject. You don't require access to individual land parcels, and the data is captured quickly. Modern computing now, it means that all of this was previously done as, long calculations or calculations running through mainframe computers. They're done in desktop computing now, and I do photogrammetry on the desktop machine that I've got beside me. But there is the flip side. So there is quite complex maths involved in processing images to remove. We also need to know and understand if we know the correct height and position of the aircraft, how precise the tilt sensors are, and the readings for every photograph. There's issues in the camera, whether the shutter speed is correct for the speed of flight. Because if it's too slow, you're going to have a blurred image. You can't use a blurred image because there's no detail. And if you put the shutter speed up too fast, you might be underexposed. Then there's errors potentially within the lens because it's made of curved optical glass. It could have distortions and such and such. And any one of those can affect that basic principle of a similar triangle. As soon as you move away from it's a dissimilar triangle and you don't know it's dissimilar, then your calculations don't work. So an error in one will lead to an imprecise output. Errors in many will compound this, and how would we actually know? So we know by looking, we know they are systematic errors. So we can look to try and work out where we can remove those errors from the subject. So tilt sensors on, a dedicated fixed wing aerial survey aircraft, their tilt sensors are highly tuned. They're calibrated. They work with timestamps. They work with a GPS positioning sensor. They understand the latency within the system so that each image has the correct correction, for want of a better term, within it. Similar rotary systems, they've got gyroscopic gimbals. So if you tell it to look straight down, it doesn't really matter what the helicopter is doing. The gimbal will compensate and it will look straight down when it's taking the photograph. Similarly, it knows where it is and it will stamp the data, the metadata, with its position. We can establish ground truthing and ground control points. Like anything, that's just good control. We can go out with GPS if we're interested in high accuracy photogrammetry. we can occupy these as we would do our primary and secondary control. If we're looking for something a little bit more quick, we can use fast static, RTK, and things like that. So once we've got ground control, we've actually got almost a check within our calculations. Previously, all those calculations, you wouldn't know if you had an error because there is no redundancy within the calculations. One on the other, but you then go, well, I've got a vertical displacement, but how do you know that is an error or if it actually does exist without going out and visiting the site? If you go out and visit the site, you're kind of undoing the reasons behind photogrammetry. And the digital sensors that we've got, they've got high dynamic range now. So essentially that is they take a burst of images all at different exposures at the same time. So you can either blend them together or you can flick through and say, right, well, that one's underexposed, that one's overexposed, but the one in the middle is perfect. It's a little bit like Goldilocks and the Three Bears. So on to flight planning. And again, flight planning is another one of these things that we have to consider if we're looking for a good output from our photogrammetric missions. So it is key to a successful mission. I've already mentioned about overlap being critical. And that our height above ground sets our baseline scales. And if you change your baseline, you're either going to have not enough detail in your image, or you have too much detail, or if you fly too close, then your overlaps are going to be much closer together. Your camera, your zooms, your shutter speed may not be able to cope with that, so on and so forth. We're also talking about a flight path for a fixed wing, which is what I'm kind of showing here. It's not just your area of interest, which I'm showing the sort of bluish colour. The aeroplane has to fly well beyond, then turn, and then fly back again, and then turn and fly. So you're talking that's quite a long area, quite a large area to fly, just for that bit in the middle, because you can't use the first and last images in each run because they have no overlap. So it does take a bit more work. And if you consider then that could be within, there could be hills on either side. If the aeroplane has to climb, that's not ideal. He can't climb when he's within the mission zone because you're going to get a variation on your ground truthing. So we'll talk a little bit about UASs, so unmanned aerial systems, or drones as they're better known. These have had a huge impact in the geospatial community. What was previously a dwindling and dying field of geomatics has really came back into the fore when drones kicked in, because it opened it up. Prior to that, we were talking about, the likes of the Ordnance Survey. They had their own aeroplane with their own massive camera, which would cost tens, if not hundreds of thousands of pounds. Plus the fuel to fly and so on and so forth. For what was essentially a mapping grade, so not a particularly accurate deliverable. But bringing in drones meant we can fly lower, slower, and if you can fly lower and slower, then you're not overly worried about the size of your sensor or the size of your focal length, because you can fly lower. Also, the higher you go, if you want to see something at 5 mil from 1,000 meters, you need quite a good zoom or a really large sensor size. But if you're going to fly at 50 meters, all of that can be much more miniaturized. So I mentioned there a little bit about the drones. They've got that gimbal on them, as you would find in helicopters. They fly at slower speeds. They're generally fitted with 3-axis gimbals to ensure that we get the perfect nadir, or when we're working off nadir, that we've got the tilt angle that we actually want to see. And whilst they are more successful for drifting off course, their positional accuracy is much better. GPS or GNSS refreshes at 1 hertz. So every second you get a new position. If you're only traveling at 5 miles an hour or 10 knots an hour, you're getting a lot more GNSS signals than you are if you're traveling at 200 knots. We can also pre-select our flight paths and things like that. So, and the image sensor is more digital. Another thing we need to consider when we're talking about payloads and whether we're using drones or various other items and just in general in photogrammetry, it's the size of the sensor. So in the past, where you had your old cameras, where you had your standard 35mm user camera, and then you had large format cameras, which were sort of taking photographs of circa A4 size. The move to digital sensors, we've now got much more megapixels, which is, in the past, it was just the film was exposed. Now it's each pixel within the sensor is turning itself on, turning itself off, picking up the luminosity, the red, green, blue signature coming from the ground. So it's something that we need to consider. The image sensor size, the quality, the quantity of the pixels as well. And we can't just go, yeah, we'll just have more of those. We'll have a 300 megapixel camera and just be done with it, and we'll get it in the largest sensor we can, because it depends on what you're trying to do. And if we start using it sort of structure from motion, which I'll go on to talk to in a few minutes' time, that uses the RGB signal of each pixel to actually look at itself and then look at its neighbours, and then try and pick that same pattern of signal in this photograph with the same pattern in another photograph. And if you've got too many pixels, because your pixel's so small that they're all just showing black or they're all just showing grey, how does that mix that? How does that match it? Does it know it's that one to that one, or does it know it's... So you get ambiguity within it. Unfortunately, it's not a case of, well, we'll just go for a low pixel count, because the lower the pixels, then you lose your ground sampling distance, or GSDs. And a GSD is essentially the smallest feature you want to locate on site. So in the image on the right-hand side, you can see there we've got a rather pixelated buffer stop. And then you've got a buffer stop probably with the right, round about the right amount of pixelization that you can see the various artifacts. If you were more interested in understanding what the chair screws were like, then we probably need to go and look at another sensor or a combination of sensors just to make sure that we pick up what we actually want to see. So ground control, this is one of my loves, because this is where photogrammetry sort of overlaps with traditional surveying. And it is, for me, one of the probably most important parts of photogrammetry. To get good results, you need good ground control. So I've got an example there of average ground control being established. You can't expect to get 5 mil accuracy out of your resultant photographs if you've got a cross that's 100 mil wide. And I don't mean about the overall length, where the intersection point is the two, because that's the point you would pick. If you've got multiple points you could pick, then you're just bringing ambiguity into your answer. Similarly, if you can only look at 5 millimeters ground sampling distance, there's no point having, a dot in the ground that's only 2 millimeters wide, because you won't see it. It'll just be swamped to the pixels round about it. And whilst we've got UAS that's got their real-time kinematic or post-processing, You can use those just for positioning the aircraft, but they don't offer any redundancy in the system, so there's no way of checking for errors. So ground control really is fairly important. You can see that the more down ground control you got, the denser your ground control is, the better you're going to have your fix. There's less interpolation, and you've got more redundancies. So if you've got ground control in every image, which you wouldn't have, it does mean that you know at that point in that image, you've got something you can check back on. You've got a redundancy in your calculation. You might only use every fifth one for a calculation of working out your heights, but you could then go into the model and click on the other points just to see just how close are you as your answer to what you believe to be true by using your ground control. So as I said, similar to surveying, control is key. I'm going to move on now to oblique photography, if that's okay. And I've said everything we've done before. We've looked at the nadir. It's all about that nadir. It's all about removing the tilts from the images, and fix them so they're ortho-rectified. Those ortho-rectified photographs, they can be difficult to interpret. You don't, especially if they've been ortho-rectified properly, where items such as lampposts have been corrected. In a true ortho photograph, you shouldn't see the sides of buildings. That should all be taken out. And if you don't have that, it's hard to understand the concept. The picture we've got here isn't too bad. We all know that the track sits lower than the platform. But can we tell if that's in a steep cutting at the terminal end? Some people might be able to tell. Some people might think it's not. It's a bit like that end corner cube that folks say, is it sticking out, or is it does it project out, or does it drop in? It's hard to tell. So oblique photography brings that. It helps remove that little bit of ambiguity, and it brings context into what you're doing. It also allows us to use a thing called structure from motion, which is fairly new, but it's been about for maybe 20, 30 years. But again, with the increase in drones, the simplicity of capturing the data, things like structure from motion have really taken off. So rather than being an annoyance, something we have to correct for, with structure from motion, we actually use those values as long as we've got them recorded and we understand what they are. Because that's, again, if you're going to remove them, you need to know what they are. Similar, if you're going to use them, you need to know what they are. And again, we need the robust ground control. So where it varies is we're not just looking at a two-dimensional plus vertical ground, and we're not just looking at a two-dimensional plus vertical flying height where we expect the flight to be perfectly level. We're going to fly at different heights, we're going to fly at different angles, and we're going to take all that data and do a thing called aerial triangulation. So we're looking at not only working out where the aircraft is in 2D plus vertical, we're looking at it in a three-dimensional aspect, and we're going to look to create a three-dimensional image from the resultant photographs that we take. Similar before, and it goes back to what I've just said, it's only as good as your ground control, because that's your truth. That's how you know that your calculations are worked correctly. Flight planning for structure from motion adds another complication. Probably a worthwhile complication, but adds another complication. So not only do we need to consider all the previous factors for nadir imagery, flight heights, focal lengths, sensor sizes, we also need to consider that we're not just taking straight down photographs, that you'll want to see sides of buildings. So have I got full capture of the front of the building? Do I have full capture of the side of the building? How do I get round the back? That type of stuff. And whilst if it was as simple as going and surveying a stadium or a building, you would just do a spiral flight up or a dome flight to capture that. We can't really do that on a railway because you would just constantly be doing little circles everywhere and not actually getting very far. So how we tend to do it with the UASs and various other stuff is we'll repeat the same flights. So we'll fly the same kind of grid pattern that we'll fly for a traditional nadir, but we'll fly it again and we'll change the camera angle, and then we'll fly it again and we'll change the camera angle again, so on and so forth until we've captured enough images, looking to the left, looking to the right, looking forwards, looking back, as well as looking straight and down. There's a balance there to be had. You could do it to the nth degree. You could get it to step up in 1 meter intervals. You could get it the camera to rotate in 1 second intervals if you wanted to, or the gimbal to rotate. The more images you take, the longer you've got the aircraft flying, and the more time it's going to process, and ultimately the more expensive it's going to be, whether that's a combination of the flight time, the processing time, data storage, so on and so forth. And you might end up with a deliverable that is that heavy in data that the end users can't actually use it. And you could do all that, and if you still haven't got the control network, you've got something that's highly rendered, but not particularly high accuracy. So kind of lapping back to the start. So a picture is worth 1,000 words, but it does take a lot of maths to get there. There's a lot of opportunities for error. And by its nature, photogrammetry is a passive sensor. It doesn't work at night. I know it seems obvious to say, but it doesn't work at night because it needs the light reflected, but it doesn't generate its own pulse and look for a return. So if it was, it differs from aerial LiDAR, in that an aerial LiDAR unit sends down a pulse, a pulse of light, and it bounces back up. It knows the wavelength that it's sent out, so it can look to the wavelength Keynes back in, and it uses essentially the speed of light calculation. It's a very simple calculation. It knows the angle it sent it out at, it knows the angle it came back in at. It knows part of the shape, the phase shift of that signature, and it works out from either time of flight or it works out from phase shift. We don't have any of these. These are just photographs. So if you don't have ground control, you're relying on understanding where the helicopter was or the aircraft was and various other stuff. So there is a lot that can go wrong, but once it's done right, it's really helpful. And we have proven, we've got suppliers out there who can, with their high quality sensors, fly at low altitude with high overlaps, and they've proven they can deliver a high accurate survey. So it's not a silver bullet. It's not going to remove boots off ballast tomorrow, but it is a very useful tool. And when it's used in conjunctions with traditional and other remote sensing techniques, so traditional survey for your ground control or picking up your rails or whatever you would do, add that with aerial LiDAR, whether it be a bespoke mission that you've asked for it to be done, whether it's the national mission from 2018, 2019, whether it's you going out with a terrestrial laser scanner or a train mounted laser scanner. You can build up on these layers, and you can build up and you can use, if you've got a traditional laser scan, you can use that as your ground truthing. So rather than you having points every 100 meters or so, you've essentially got millions of points. The more points you've got of you know for truth, the more accurate your photogrammetry becomes. So getting close to the end. So this is hopefully this is the less dry part. So standard topographic survey. As I said, you know, if you understand, there's back when I did non-CAD stuff, we used to put little tadpoles on them to tell you if that was a cutting or a banking. So without seeing the values, you go and say, well, I'm on a banking, I'm on a cutting. It's hard to say. What else is round about me? So this is where just standard photographs or photogrammetry, you know, orthophotographs come in really handy, because you can see there, that's where we are. We can now see we're actually in an urban environment. We can see that there's, you know, another track there which we hadn't surveyed. So there is things that we can see, and it does bring in context, and it will help remove that requirement for folk to go and visit sites as often if we have good quality recent photographs. So things like route view become really invaluable. This is a little video. I have no idea if it's going to work or not. So what I'm going to do just now is I'll turn my camera off and free up some bandwidth. And if somebody can tell me if it's working or not, once I press play, that'd be really appreciated. So you should start seeing it moving now.
Yep, we can see it.
Fantastic. So I'll talk over it. So this is essentially what we've done. This was a drone flight, and this is structure from motion actually in use. So you can see there we've now got our sleepers. We can see our sleepers. We can see our cant markers. A traditional straight down view, but rather than being like an ortho-rectified where you wouldn't see the sides of buildings, we can see the sides of buildings. It gives us a context that we're again we're in an urban area. It's a false cutting, essentially. We've got a passing public highway going over the railway, adjacent to the station. We can zoom in, we can move ourselves round about, and we can measure roughly from this. So it's one of the advantages. That's quite a big advantage of where we can be going with structure from motion, and where photogrammetry is really adding value now. Things like this means that we don't need to go to site that often. We can have our access points. We could have this available to our LOMs and our MOMs. You know, if they're having to go and respond to an incident or something where they've not been to recently, they can go and look at that and understand where, get their bearings, get their orientations, look for any potential hazards before they actually set foot on site. So it is something we can use to help folk, help in our challenge to, you know, eliminate the risk of people being struck by, or workforce being struck by trains. I'm not sure how long this spins on for. That's that one. So this is another little video. This is showing, again, similar structure from motion, but it's showing it in a design engineering context for capital delivery projects. This is an electrification project I was helping support in Scottish Borders with our supplier SPL at the time. And we actually found that working with SPL, the designers, and this is on a Bentley iTwin solution, that we were reducing the requirement for folk to actually go and visit site to do their planning. So I'll just press play on this one. It should start moving. It's not moving for it, it's moving now. So you can see there we've got survey. That survey came in from Ryler. So we're integrating two sensors now. And the overhead line stuff you see there comes from the CAD model. So we're introducing the CAD model into the into this 3D environment. so that we can see what it's going to look like. Look for potential construction issues, look for potential, you can see there that pile in the bottom right hand corner is catching the troughing route. We can see how these things might potentially interface with maintenance activities and various other stuff. So it does become quite powerful when you put it into the sort of context of what we can do next. I think that is the end of my presentation. Yes, that's me.
Yeah.
So I'll stop presenting.
That was amazing, Colin. Yeah, the future again is just so many opportunities in there. Do we want to put our hands up for come in and ask Colin some questions? Put some hands up or drop them in the chat and I'll read them out. Peter, go ahead, Peter.
Hi, Colin, super talk. Really enjoyed that. Thank you very much. Can you tell us, because you didn't mention it, at what point do you have to take into account curvature of the Earth and corrections for curvature of the Earth? Have you got a particular scale that you disregard it at, and then a scale beyond which you have to compensate for the Earth's curvature?
Yeah, generally we'll take it as 10 kilometers. However, we're dealing with mapping. If we're predominantly dealing with mapping, it's less of an issue. When we're measuring inside these types of things, I'm trying to work with the suppliers so that we only get it to 1 or 2 decimal places. The curvature becomes, when you want that whole engineering scale of 1 millimeter on the drawing is 1 millimeter on the ground, that's when we're starting to really try and fix that in. But these are generally between 25 to 50 mil. But there's nothing stopping us, as mentioned earlier, about ground control. That ground control can be OS based, but it could be your project grid based, which is done through a snake grid, which has that flat earth essentially. So you've taken out that distortion. But in a rule of thumb, generally 10K, because that's what our OS tiles are in 10K chunks. After that, you have to multiple scale factors.
Thank you. Thanks very much.
Cheers, Peter. Andy, you got a question, please?
Hi, Colin. It's less of a question than a couple of comments. First of all, thank you very much for the presentation. It was very interesting. I started in the industry 53 years ago, and I still remember being shown the Lancashire and Yorkshire Railway 4-screw level. So to have gone from that to what you've seen in this length of a career is quite amazing. The other comment, bearing my ex-RAIB role in mind, is although your presentation was very much about the technical side of it, it is such a benefit for staff safety and, as you said, getting people away from the running line to do surveys and work forward. And it's, I've just done so many investigations into staff fatalities over the years, and it's a real plus to get that. So no question, but thank you very much, and 2 particularly interesting points from a personal point of view.
Yeah, just on the whole safety element of it, there is other techniques that we can use. So we've got train-borne surveying, but those generate point clouds and they're quite hard to read. So this brings in the context. So yeah, it's one of those things that when we bring them all together, we should be able to reduce the amount of times people have to go on site, which ultimately reduces the risk for fatalities.
Brilliant. Thanks, Andy. Anybody got any other questions? No, it doesn't look like. Colin, I think that's just testament to how detailed and in depth that was, and took me to a new level. I thought he was on my level when we started off talking about dog ears and noses, and then bell towers and the Wright brothers. I thought that was good, great analogy. And then stereoscopic parallax, and then ground control. Just yeah. So well, I didn't realize there was so much involved to get those pictures, and I've seen them and they are amazing, and things are moving on so quickly, but I didn't realize there was so much calculation to get it all done. So yeah, and then those videos with that structure for motion, they're brilliant, and the planning that has to go into it, just and as Andy said, you know, to the safety benefits are just you know, huge, and yeah, so I'd just like to invite everybody to you know, to thank Colin in the normal way. Well done, Colin.
Thank you.
Right. Cool. So that makes our last presentation for the 22-23 season. So we'll be back in September, and we'll be in touch with dates, etc. as we go. So thanks again, Colin. That was really great. Cheers, everybody.
Cheers. Thank you.
Cheers. Thanks.